Okay, we're going on to part two of chapter 20 on of conceptual physics on sound. Um, Let me dismiss my image and we're going to talk about sound in air. Uh, Sound waves are vibrations made of compressions and rarefactions. They're longitudinal waves. They require a medium and travel through solids, liquids, and gases. So here they're showing. Let's say you have this big room with just one window, and there's curtains in the window. When you open the door, you generate a compression wave that uh, travels down, and it actually uh, kind of blows open the window curtain. Um, the so it's a longitudinal wave. It's not going up and down or side to side. It's pressure going this way. Uh, so it's a pressure wave that goes down this way. When you close the door, when you close it, you get this rarefaction that travels down in the same direction and causes the uh, curtain to move inward. So if you were to open and close it, open and close it, open and close it, you would get this compression wave and this rarefaction wave. Compression, rarefaction, and you would see the curtain blowing in and out, blowing in and out. So they're longitudinal waves. They require a medium. If you were to have a vacuum, the you would um, you would there would be no sound in a vacuum. In other words, in a vacuum, there's no air molecules to vibrate, so the sound wouldn't transmit. There's no molecules to compress and rarefy, so you wouldn't hear anything in a vacuum. So it does require a medium, and it travels through solids, liquids, and gases. We discussed that in the last section. Um, in air, it's about 300. Uh, they use 330 meters per second. That's, I think, at 0 degrees. At room temperature, it's more like 340 meters per second. In water, it's much higher, and in metal, it's much higher, even still. Okay, this is an image you see as the tuning fork, as the tines of the tuning fork, as it goes out, it causes a compression wave and it moves back. It has this rarefaction. So it's a compression, rarefaction, compression, rarefaction, and they even list it here on um, the top and the bottom. So the wavelength of sound is the distance between successive compressions or rarefactions. So this is a peak, this is a trough, this is another peak. So this is a one wavelength. Okay, let's see. How sound is heard from a radio loudspeaker. Radio loudspeaker is a paper cone that vibrates. What you have, let me, what you have is you have a coil of wire. You have a paper cone attached to uh, a coil of wire, and you can do it either way. You have the cone attached to a coil of wire, and there's a magnet in it, and as the signal goes in and out, whenever you have current in the wire, it creates its own magnetic field. So the permanent magnet and um, the magnet, the electromagnet that you've created forces the cone in and out, and it produces a sound. So this is the vibrating loudspeaker, and it sends out these compression and rarefied air molecules that hit the microphone, and then it is shown on an oscilloscope. And I just happen to have in my phone a little, I think it's called Sound Beam. And let's see, let me stop the share where you can see hopefully you can see it. Now, if I can get it, let me see if I can. I get a lot of. You can see my voice as I speak. You can see the waves on the oscilloscope. Now, when I did the experiment with the straw, the soda straw, or the straw in my cup, I didn't hear anything. So I don't know that it's the whistling is coming out on the video. I hope it is. But anyway, this is what the waves look like as I'm speaking or as I whistle. There you go. And that is a demonstration. Where's the PowerPoint? Here it is. That's a demonstration of what they're talking about. This, instead of a speaker, it's my voice. So I'm causing compressions and rarefactions to go to the microphone of the iPhone, and then it shows you the little waves on the oscilloscope. Okay, I think that's it for no, there's more. I'm sorry. I thought, okay, no, we're still going. I thought it was the end of the chapter. Okay, any elastic substance. Let me dismiss this because it's covering up part of the slide. Any elastic substance, solid, liquid, gas, or plasma, can transmit sound. In elastic liquids and solids, the atoms are relatively close together. They respond quickly to one another's motions and transmit energy with little loss. Sound travels about 4 times faster in water than in air, and about 15 times faster in steel than in air. So that's what I've been saying. It's 330, 340 meters per second. We're talking about 1,000, maybe 1,200. Even 1,500 meters per second in water, and then we're talking about 3,000 meters per second in steel. So it's much faster in metals. Oops. Okay. The speed of sound depends on the speed of sound in air. Now we're talking about the speed of sound in air. It depends on wind conditions, temperature, and humidity. Speed in dry air at 0 degrees is about 330 meters per second, and about room temperature, 20 degrees C, it's about 340. Water vapor in the air increases speed slightly, and sound travels faster through warm air than cold air. Each degree rise in temperature above 0 degrees C, the speed of air increases by 0.6 meters per second. Speed in water is 4 times the speed in air, and speed in steel about 15 times its speed in air. Let me just pull out a calculator, and we'll just I'm going to put 340 because that's what it is at room temperature. So 340 that's 1360. 1,000 in water, it would be 1,360 meters per second. In steel, 15 times is 5,100 meters per second. The sound travels in metal. Okay, there's all right. Okay, you watch a person chopping wood and note that after seeing the last chop, you hear it 1 second later. How far away is the chopper? 330 meters, more than 330 meters, less than 330 meters. There's no way to tell. No, it's 330 meters. I'm assuming it's about 0 degrees C. You're out in the cold when you hear that. That's why the person is chopping wood to warm the fireplace. So there it is, 330 meters. Now, you hear thunder 2 seconds after you see a lightning flash. How far away is the lightning? Well, if it's 2 seconds and it's 330 meters per second, it would be 660. And there it is, 660. When I worked at Southwest Research, one of the things that we did, we were blowing up concrete panels. I was just an observer. I wasn't the one that was um, planting the explosives, but I did observe the blowing up of these concrete panels in pits, and you would let me go ahead and actually I think that's the last one, yeah, in part two. So let's stop the share. You would I don't know how far we were. We were probably um, half a football field, 50 50 meters or so, and when they would ignite the blast, I don't know whether it was C4, it wasn't dynamite, I forget what. It was a plastic explosive, and the concrete was in a pit. They blasted, and you'd see this plume come out from the pit, and then I wish I had timed this, the number of seconds it took to get to our ears. This is a long time ago. This was probably in the 90s. You'd hear the blast. So you'd see the plume, a delay, and then you'd hear the blast. In fact, you'd get a percussion wave from the blast. Anyway, that's just a little side side story. Okay, and I think that's it for this section.